turn it in, guys.
Good afternoon, welcome to Chemistry 401. A couple of announcements before we get started. First off, homework for Chapter 16 is not due this Wednesday, it is due the following Wednesday, so you now have 9 or so days to get it done. I apologize if it caused you any anxiety or otherwise for having that much work to do in such a short period of time. However, now you have more time, and of course, happy to see as many people who want to come to office hours tomorrow as possible. Kate?
What about the kinetics lab too?
What about the kinetics lab? Great question. I have told my students that they may turn in the lab next week for full credits, and I will pass that along to Professor Segru. And what I will say is part of the reason that can happen is because this week's lab is completed in lab, and so my students completed it and I graded it before any of them left, and that was a requirement for leaving. So look for that as well. And to prepare yourself, please do your safety. There's a lot of chemicals ahead of time. Otherwise, that can take a while and slow you. Second announcement. The requirement to get extra credit for being in a study group is that at the first, second, and third exams, you turn in a study group log documenting the times you have met, who's been there, and what you did. I have received either 3 or 4 of them. If you are in a study group that has not turned one of those in, I need to see that by Wednesday in hard copy format, please. Any questions about that? One other tiny announcement, and this is not an extra credit opportunity. However, I will be talking about the class, The Science of Coffee, at Sac State this coming Friday as part of their Department of Chemistry seminar. I don't remember the room, but it's, I think, 1 to 2 p.m. So if you're interested, please feel free to attend. But it's not an extra credit assignment. You attend because you're interested. With that, comments on the exam. My comments, anyway, was that scores overall were good. I do not expect a curve. High was 140 points out of 150. There was a 140 and at least 2 138s. So scores were generally good. Other things I will say is that if your score was not as high as you would like it to be, this is an indication that more work needs to be done, or better or more efficient use of your time. It is always a useful or efficient way to spend your time, if you can, to come to office hours, but that's not always possible, I know. And it may be time to find a tutor on campus or elsewhere. Anyway, the other thing I'll say is if you check your syllabus, and this is the same as if you were in my Chem 400 classes, any one exam can have its percentage replaced with your percentage on the final if it helps you. And so nothing is critical right now, although in general, somebody asked me this, are the exams going to get easier or harder? And I think they're going to be about the same. So, but since your future exams are mere figments in my imagination, I don't know for sure yet, but I'll keep you informed as they get closer. Any questions before we get started? Well, while we were prepping for exam number 1 on chapters 14 and 15, we did all of the lecture for chapter 16. Chapter 16 can be summed up as sort of what it was about, was what are acids and bases, and how do you calculate the pH of a weak acid or weak base solution. Now we're going to use that right away in chapter 17 on the topic of buffers. And our first definition of a buffer, or a buffer solution, is that it must contain significant amounts of both a weak acid and its conjugate base, or a weak base and its conjugate acid. If you remember from last time, we said that if you are a weak acid, your conjugate is a weak base. So weak acid goes with conjugate weak base. We said that strong acid, or base, let's go with strong acid. Strong acid has an inert conjugate base. And so buffers will always involve weak acids and their conjugate weak bases. I have a reaction written here. So far, it is a Ka reaction. We know it's a Ka reaction because we have what we recognize as a weak acid right here. Weak acid plus water goes to hydronium plus conjugate weak base. And this will always be true for a Ka reaction. Other things you need to know about buffers. Well, first off, buffers resist changes to pH. And now I will tell you how they do that. Buffers resist changes to pH by turning strong acids into weak acids and turning strong bases into weak bases. And by turning, I mean reacting. So let me turning means reacting. I mean, that's all chemistry is about. I don't know why I wrote turning there, and then I wrote it again, but reacting. Maybe I'll even cross those out. And what we will see, and we will talk about why this is as we come up, but if you have a reaction involving the, what's this? Sodium hydroxide. Right, because you add a strong base to a buffer. That strong base will react with the weak acid. And these are aqueous. Do you see that arrow? Is that a double arrow or a single arrow? That is on purpose because this reaction goes 100%. When I say I will prove it, I will prove it later in this chapter by calculating the Kc value for this reaction. And we will see it is very large. And so, we won't do it yet. We're still talking about buffers and how they work. But we will show this is true. The products on this are just like from chapter 16. If you have an acid and a base, the acid donates a proton to the base. We get, well, we'll turn that into a hydroxide ion, and the sodium will be a spectator ion. Hydroxide picks up a proton, NH+. Nothing up my sleeve. We have just turned a strong base into a weak base. We have turned the strong base, sodium hydroxide, or the hydroxide ion, into the weak base, acetate. And I'll write that, turned or reacted hydroxide with the weak acid in the buffer to make the weak base acetate. Reacted hydroxide, which is a strong base, question. Reacted the hydroxide, which is a strong base, Sb stands for strong base. With acetic acid, a weak acid, to make the weak base, or the conjugate. to make acetate a weak base. Voila, nothing on my sleeve. Now you have just a weak base. And we'll leave it with this example, but from what number 1 says, I could have done something similar with a strong acid in the weak base as well, and we will see that as we go. Question?
Is the hydroxide reacting directly with the acetic acid, or is it reacting with the hydronium ion the acetic acid has?
Great question. Is the hydroxide reacting with the acetic acid or just the H plus here? So or with the hydronium, I think that's what you said, right?
Because the concentration of the hydronium ion is going to be different from the concentration of the acetic acid.
Great question. Here's how this goes. So if we had a solution of a weak acid, that weak acid would make some hydronium and you'd get a pH, right? That was what all last chapter was about. And so you can think of this dissociating into hydroniums, and it's the hydroniums that react with this. Although that will be a longer path than necessary to solve this problem. What I would suggest is that, as we will see on the next slide, when given things with concentrations, it is always best to start working with those things. Though you've brought up a very good point, which is it is more complex than that. And I will answer the question even further, which is underlying everything we do with equilibrium and equilibrium constants is that we were always dealing with the largest K value first, and that will always be fine. What I mean by that is when we calculate the K value for this reaction, it will be 10 to the 5th or higher. That's plus 5, that's big. When you deal with the K value, the Ka value for acetic acid, it's 10 to the minus 5th. So deal with this later as a weak acid. Does that answer your question? Yeah, good question. Any other questions? Okay, well, there's more to this, and I was working on homework number 4. I'm writing up the key to make sure all the questions are hopefully rock solid, but then I should have it for you on Wednesday. You're still working on homework number 3 anyway, but it should be available to you by Wednesday. And one of the questions will say, tell me everything you can about buffers, and that will be like a paragraph. Here's a couple of the things that you know already. Okay. So now calculating the pH of a buffer. What is here's an example question. What is the pH of 250 milliliters of a buffer made from 0.100 molar acetic acid and 0.100 molar sodium acetate? First question you always ask with a buffer. Do you have a weak acid and its conjugate weak base? Please answer if you can. Do we have a weak acid and a conjugate weak base? Yes, we do. Then we have a buffer. All right, weak acid, Wa. I will cross out the sodium ion, which is a spectator ion, and leave the acetate ion. And all of those spectator ion things and nationic things that we did in Chem 400, now's when knowing them helps. Because if you leave that sodium in there, it's less clear whether you have a conjugate pair. Any questions about that so far? One other thing I'll point out. I used weak base here, and I used conjugate weak base here. The C is for conjugate. And those are terms, like, we will need to know on site, by looking at compounds, what kind of acids and bases they are. And we will talk about them enough that we need abbreviations for them. All right. Okay. So now I've set up this ice table here. Question, Kate?
How can we drop the H on the base without having added H on the base? I don't know why.
Good question. So sometimes we drop the H on the base, and sometimes we add an H on the base. And the short answer is typically we drop the H or the H plus. Although, if you're talking about something like this is an acid and this can be a base, and it has an H on it. So what I would say is, for buffers and everything we're going to do, the one that has the H is the weak acid, and the one that doesn't have the H is the conjugate weak base. But if you have a case like this, you would want to ask the question, what else is around? If H2CO3 is around, then this is the conjugate weak base. If CO3 2 minus is around, then this is the weak acid. So a lot depends on what's around it. And we can talk more about that if you want. But that's the general schema. Right? Everything is relative. Or things are getting increasingly relative. You need to say, what do I have? And then you need to look around and say, what else is around? Okay. But, okay, so here we have a Ka reaction. Here we have a Ka value. This looks very similar to some of the things that you're doing on your Chapter 16 homework, except on Chapter 16, these are both zeros. This time, only this one's a 0, and we typically write approximately 0 there. It's 10 to the minus 7th molar in a neutral solution, and we haven't run into a case where this is really different than 0 at all. Which way should the reaction go to get to equilibrium? It has to go towards products because there's a 0 on the right, even though there's another number there. So and we've actually done a couple ice tables like this already in Chapter 16, but here's another one. Our Ka value, which I'll write here in a second, is equal to our products over our reactants. All of our coefficients are 1s. Our Ka value is sufficiently small that we can ignore x. When we ignore x, and again, we can ignore x when it's subtracted off something larger. We can ignore x when it's added to something significantly larger. So we'll set both of those equal to 0. From there, we have a 0.1 and a 0.1 on the bottom and the top. And I get x equals 1.8 times 10 to the minus 5. When I add x back in, does it make a difference? It does not. So, our concentration of hydronium is just 1.8 times 10 to the minus 5th. That's our x value. And from there we can calculate our pH, which is 4.74. Where all we did was, of course, to get pH, take the negative log of the concentration of hydronium. We also know that our concentration of acetic acid and our concentration of acetate are still 0.1. Any questions about this? If not, what we're going to do now is we're going to derive an equation that is good for calculating the pH of all buffers. It's called the Henderson-Hasselbalch Equation. Sometimes shorthand is referred to as the HH equation, at least in my class. And this is going to be a general derivation. What that means is my acid is going to be HA. And I'm going to write a Ka reaction. So plus water goes to hydronium plus A minus, where A minus is my anion, also called my conjugate rephase. And this is a molarity ice table. And what I'm going to put right here is concentration of HA initial. So that's going to be square brackets. And I'm going to have the subscript I here for initial. This is my initial concentration of my acid. Nothing for my liquid, approximately 0 for my hydronium. And just like here, there will be an initial concentration. It'll be concentration of A minus initial. Do my minus X, my plus X, my plus X. Ooh. Except now I'm going to put plus concentration of hydronium right here. And that's because, like we saw in the previous problem, X is our concentration of hydronium. Did these X's matter before? What happened to X over here? It was insignificant. That will always be true, so I'm going to write just the concentration initial here, then I'm going to write assumes X is insignificant, which is always true. And in proper documentation format, we'll put an asterisk there, we'll put an asterisk there, because the asterisks refer to this point. Alondra?
What did HA and A minus stand for?
Oh, HA is the generic formula for an acid. And to say a little bit more about that, this buffer stuff will only work for weak acids, we will see. So technically it has to be a weak acid. But, I mean, the setup is actually general. And so A minus is the base. Yeah, good. So this is a Ka reaction, so we can write our Ka, we can write products over reactants. And now comes the fun part. Take the minus logarithm of the whole equation. If you do that, you get minus log of Ka equals minus log of hydronium over minus log of the other quotient here. Everybody okay with that? If you're okay with that, then let's keep going. What is this thing right here? This is pH. What is this thing right here? Did I define this last time? It might have been a blur. Hopefully I did. I'm going to tell you that whenever you take the minus log of something, it's called P. So this is going to be what's called the pKa. And this is just minus log. No changes there. Certainly not anything up in the center. Because all we're going to do next to get it into its final form is we're going to move this to the other side. When I do that, it will become positive. And since I'm interested in solving this equation for my pH, I'm going to put pH equals pKa plus this term. And that is our final form. If you know the pKa, and you know the logarithm of the concentration of the conjugate weak base and the weak acid, you can find pH. And I'm going to do one more thing. I am going to actually write a new version of this over here that says pH equals pKa. Plus log conjugate weak base over weak acid. Oops, I've done it again. I've forgotten my square brackets. That was on purpose, actually. These are concentrations, and concentrations work in this equation. Concentrations work, and that's how our derivation was done. But every single time you make a buffer, you're going to have the weak acid and the weak base in the same beaker. Which means that if you know the moles of weak acid and the moles of conjugate weak base, this equation works as well. The volume will be the same for both of those. So concentrations work, moles work as well. And that's why I've left off the concentration brackets there. You can put them back in, or you can, you use this equation 50 to 100 times by the end of the class with moles or molarity. And of course, if you know your volume, you can always turn moles into molarity and vice versa anyway. And at different times, say in this problem, you'll be given molarities, but later on, maybe you'll have moles. That's why I'm harping on this point. Okay. Questions? Travis? Does that warrant a box? That, you know what this warrants? A rhombus. Actually, I don't even know if that's a rhombus or not. It warrants a box for sure. It warrants 2 of them because that's really what you're going to use. The derivation is nice and all, but all the derivation shows you is that the Henderson-Hasselbalch equation is a shorthand notation for a Ka ice table. And so now you'll stop doing Ka ice tables for buffers. You will just use the Henderson-Hasselbalch equation. Letter L is my arch nemesis. And there's a couple of them in there. I know, right? I have 4 of them in my name. All right. Does that answer your question? Other questions?
So this works because we're assuming that Ka is small for all of these. buffers.
Good point. This works because we're assuming Ka is small for all of these.
Okay, that's why it works across every single buffer.
Every single buffer.
Okay.
So a further note, Elliot, to not all, like, there are a couple weak acids that are above that 1.0 times 10 to the minus 4th range. And this equation works for them too. If this was a 0, then we'd have to worry. But since there is some weak base here, that actually means that for all weak acids, you can ignore X. So, I don't know, that's probably worth noting too. Works for all weak acids, regardless of the 1.0 times 10 to the minus 4th thing, approximation. So anyway, we will always use this for buffers. How about that? Always use for buffers. Think you can't use it? You're wrong. Anyway, yes?
Can you give us that range again for the Ka for what is the weak to the strong?
Sure. Question, what's the range of Ka values for weak acids? Well, let me start there. Ka range for weak acids is from less than 1 to 10 to the minus 14. It's a wide range. All right, so now we've got the HH equation. This is the same problem, except now we're going to use the HH equation. And let's just start by writing it down. Oh, my process. We have a weak acid, we have a conjugate weak base, we have a buffer. Always use the HH equation for buffers. So we'll write it out. This particular time we do have concentrations. So you can put in the brackets if you want. You don't need to. We're all adults here. What you do have to do is you do have to look at what your acid is. You do have to look up its Ka value from the conversion equation sheets. We use acetic acid a lot. Its Ka value 1.8 times 10 to the minus 5th. Take the negative logarithm of that, you get the pKa, 4.74. Our concentration of weak acid is 0.1 molar. Our concentration of acetate ion is also 0.100 molar. Can anybody help me? What is the logarithm of 1? 0. And when the concentrations of your weak acid and weak base are the same, your pH equals your pKa value. 4.74. Log of 1 is 0. That term drops out, 4.74. Was that the same thing we got last time? Oh, good. My notes say it is. And that's a lot easier as long as you know you have a buffer. Any questions about this? All right. What happens when strong acid or strong base is added to a buffer? Well, let's do it. So now we have the same buffer we had before, but now it says what is the pH of a buffer when 10 milliliters of 0.1 molar sodium hydroxide, strong base, is added to the buffer from the previous problem. Step 1, allow the strong base to react with the weak acid. I apologize for that. Allow the strong base to react with the weak acid in terms of moles. Nothing changes from Chem 400. It's moles that react. If you remember way back to the titration pH plot that we did in Chem 400, if you were in my class, these calculations will look very similar. For the strong base, we have 10 milliliters of 0.100 molar. That's 10 milliliters converted into liters. We're going to learn to ignore that sodium ion. You can include it for now, but what we need is that hydroxide ion. You can do it here. You can do it whenever you want to. We get 1,000th of a mole. Space gets a little squinchy here. I apologize for this, but we're going to set up a mole lice table this time, where we will calculate the moles of our acetic acid the same way. We have 250 milliliters, we have 0.100 molar. Convince yourself. You have 0.0250 moles of acetic acid. Those will react with our 0.00100 moles of hydroxide. This reaction will go to completion. That is the single arrow there. Again, we're getting to calculating the K value for this. We have an acid and a base. We will move the proton over. We also add 0.0250 moles of our base. Have we done mole ice tables before? If we have, I don't remember. Mole ice tables are for when your reaction goes to completion and we're trying to find our limiting reactant. So I'm going to write a little note over here. Mole ice table for reactions that go to completion. Molarity ice tables will be for ice tables that don't go to completion, and they'll typically have X's in them. This ice table will not have X's. This reaction goes to completion, and our hydroxide is our limiting reactant. Why? Because there's less of it. And I'll make a note right here, hydroxide is our limiting reactant. And do you see that 0 there? Is that true? Can we ever really get 0 in the fact that this is going to be coming to some sort of equilibrium as well? Well, if you write 0, it's fine with me, but I'm going to write squiggly equals to 0. Just like I used to write squiggly equals to 0 as initial concentration for hydronium. Anyway, do the subtraction. This is where I check my notes. 0.0240. .260. Still got a buffer? I don't know. Do I have weak acid and conjugate weak base? Yes, I do. How do we solve that? Calculate the pH of the buffer using the HH equation. The HH equation, pH equals pKa plus log. And this is the first time that we're going to use moles instead of molarities. You could convert these back into molarities and you'd still get the same answer. My pKa, still the same as before, 4.74. Whatever units they are, of course I write them, but they're moles this time. And then you do the log, you add it, you calculate your pH. And you should get 4.77. And here's where we talk about what a buffer is and what it does. A buffer contains relatively equal and relative, so concentrations or moles of weak acid and conjugate weak base. A buffer turns a strong base into a weak base, and when it does that, well, the pH does change, but not very much. That's what a buffer does, and that's how it is. Any questions about this? Okay. All right. Well, buffers are not perfect, and we're going to now ask the question, what happens when more strong acid or strong base is added to a buffer? What is the pH of a buffer when 30 milliliters? We're going to change this number to 300 milliliters. Because we're finished screwing around. Of 0.100 molar sodium hydroxide. Again, we're going to allow the strong base to react with the weak acid. That means we're going to do a mole-wise table just like this one, where everything's the same, except instead of this number here, we're going to put the current moles. Current moles will now be 0.03. Mole-wise table, same reaction, same two initial values here, different value there. Of our two reactants, which one is limiting? This time the acetic acid is limiting. And you also, same thing you would do for any limiting reactant problem, you subtract the limiting reactant amount. Oh, that one's not 0, thank you. Is that better, Matt? Thank you. And this will be a common theme. Do some sort of mole ice table for a reaction, and then evaluate what you have. That looks like a strong base to me. That looks like a weak base. First question, do we have a buffer? No, we do not. So you cannot use the HH equation. Still got a buffer? No. Great, use the H, no buffer. Then look at what's left. Because you'll still be asked to calculate the pH. You just got to think of what to do next. And so no, I'm so emphatic today. No. Should be disappointment, actually, because I know how to solve it. All right. Oh, now we have a strong base and a weak base. Which of those two do you think is more important? The strong base. The strong base is more important even though there's 10 times less of it, because the K value, the KB in this case, is so much larger and so ignore the weak base. Only the strong base matters. Find the concentration of the strong base, calculate POH, and then pH. And so now let's do that. We have a little bit of space down here. We know the moles. Now let's do this. Concentration of hydroxide equals moles over total liters. We have 300 milliliters. We have 250 milliliters. We will have 550 milliliters. I'll write it into this equation so you can see me adding them up down here, because you always have your total volume down here. I get 0.0091 molarity hydroxide. A pOH of 2.04 and a pH of 11.96. And that calculation is very different than the buffer calculation. But this calculation is actually identical to something you did in my Chem 400 class when you did pH titration plots. Take the leftover base, find its concentration, find pH. Any questions? Aaron?
How did you get that 2.04?
How did I get this 2.04? Good question. So I know the molarity of my hydroxide. P means take the negative log of the hydroxide ion concentration, just like you would do for calculating pH. The reason we did this is because we know that we have more hydroxide, so we have to do this one first.
So it's just the negative log of that.
Just the negative log of the 0.009. Any other questions? Angel?
So the buffer has a limit?
So the buffer has a limit. I think we all have limits, Angel. And so do buffers. So, no, it's a very good point. And we had, it takes quite a bit, right?
Yeah.
But yeah, so it does have limits. Buffers, and we will talk about this, we will talk about how good a buffer is. How good a buffer is depends on how many moles of weak acid and weak base it has. So if you want a better buffer, one way is to make it have more moles of your weak acid and weak base. Any other questions? Now let's do a comparison, the difference between having a buffer and not having a buffer. What is the pH of a buffer when 10 milliliters of a 0.100 molar sodium hydroxide is added to, well, this is the same buffer we had on the previous pages. And what we saw was that before the sodium hydroxide, the pH was 4.74. And after the sodium hydroxide was added, it was 4.77. And we said the pH changes. And this is a point that I think I forgot to make earlier. If you add sodium hydroxide to something, the pH is going up. It's just going up a small amount. Right? If the question on your next exam says you add sodium hydroxide to anything, Does the pH go up? Your answer is yes. It may only go up a little bit, but it always does. Water with a pH of 4.74. Well, this is not a calculation that we typically do, but before sodium hydroxide, we are stating that the pH is 4.74. That's the starting point that's given. After sodium hydroxide, the pH equals 11.59. And again, that is not a calculation that you have to do. I'm happy to go over with how to do that during office hours. It's not on your exam. But I want to demonstrate the effectiveness of buffers. This is a small change in pH. This is a very large change. Buffers buffer or minimize the changes in pH when strong base or strong acid is added. Any questions about that? David?
So on an exam, and there were two options we could choose from where NaOH would make the pH skyrocket or change by a little bit. Would it be changed a little bit? Like there would be no wiggle room.
If there's a buffer, and the question is, sodium hydroxide is added, how much does the pH change? We see that the pH can change a lot, so maybe you would have to decide how much of the strong base is added. But typically, for a buffer that is a good buffer, the pH won't change very much. So your question is sort of specific to exactly what the numbers are. But typically buffers, or you could say, buffers will change less than water, always. Any other questions? Well, and this next slide, buffer capacity, comes back to, Angel, your question. Buffers, they're good, they're not perfect. And how do you make a buffer so that you can exhaust them? What we will look at now is a good definition of buffer capacity, or how good a buffer is. A buffer is considered to be able to stabilize the pH within plus or minus 1 pH unit of the pKa value over what range of concentration of conjugate weak base to weak acid is this? Or it doesn't have to be concentration, just ratio of the two. Could be moles. We'll come back to the Henderson-Hasselbalch equation. pH equals pKa plus log of conjugate weak base over weak acid. And the criterion says plus or minus 1 pH unit. So for this particular test, we'll use the same pKa we had before. We'll plug in 5.74 here. And we'll now solve for this ratio. We'll put the 4.74 on the other side. We'll get 1.00 equals log of that ratio. If I want to get rid of a log, what do I have to do? I have to do 10 to the both sides. What I get? Is that this ratio is a ratio of 10, meaning that an effective buffer has a ratio of conjugate weak base to weak acid less than 10, so an effective buffer has a ratio of base to acid less than 10. And greater than 0.1. And if this were a math class, that'd be a terrible way to write it. So let me rewrite it. The ratio of base to acid is greater than 0.1 and it is less than 10 to be an effective buffer. And buffers, we did a calculation like this. They can be what's called exhausted. That means you've run out of either the weak base or the weak acid. True. And then this statement here is additional buffer capacity increases with increasing concentrations of the conjugate weak base and the weak acid. That gets back again to Angel's point. If you want a better buffer, a buffer that minimizes pH changes more, have higher concentrations. A few words about the principal blood buffer, the carbonic acid bicarbonate buffer. How many people are familiar with the fact that this is the principal blood buffer? Anybody? Raise your hand. 1, 2, 3. Okay, good. This is new and good information. The pH of human blood is 7.4. Does that sound familiar? Did you know that? So, it's not a biology class, by the way, so don't get any ideas. What is the ratio of conjugate weak base to weak acid in blood for this buffer? And just to be aware, there are other buffers going on. This is the principal one. We're going to assume for this calculation that this is the only one to keep things simple. But it's a reasonable approximation, I'd say. All right. Well, does the problem have the word buffer in it? Yes, probably, starting with Henderson-Hasselbalch Equation. Just slow down every time I say it. To solve this problem, you have the pH, but you need to know the Ka and the pKa of your weak acid. Here's your weak acid. You can look up the Ka value from your conversion and equation sheet, and I will again encourage you to do your homework with the conversion and equation sheets so you are familiar with finding these. They're in your Hitchhiker's Guide. You get Ka equals 4.3 times 10 to the minus 7. For a pKa of 6.37. So what we're going to do is we're going to plug in, just like we did over there. We're going to solve for the ratio of conjugate weak base to weak acid in your blood buffer. I'll put the parentheses around it just so you know in this case, we're solving for that. I get 1.03, I 10 to the both sides. And I get that the ratio of conjugate weak base to weak acid is equal to 10.7. And just to be clear what that means in your blood at any given time, there's 10.7 times more bicarbonate than carbonic acid. That's what that means. And according to the information I gave you on the previous one, that said to be an effective buffer, you have to be between 0.1 and 10. According to most definitions, the blood buffer is a crappy buffer. You would not want it, but this is not most situations. So the question we're going to ask is, why is this the ratio? Does anybody know why? I will tell you then. The principal reason is that your blood, the principal thing that can change your pH, although not the only thing, the principal thing was what happens if your stomach acid gets through the lining of your stomach and into your blood. That's called an ulcer, I believe. You don't want ulcers. They're pretty painful, I hear. But if they do, you want your blood to still not change pH very much. And so if you have a lot of weak base in there, the pH won't change very much. So why is this the ratio? The answer I'm going to put here is that stomach acid is the principal challenge to the pH of blood. Does anybody know what acid is the stomach acid? HCl. Principal one. It's got hydrochloric acid in it. So, is that a strong acid? Yeah. Yes, very strong, or certainly strong. So HCl is in the stomach. And if you remember, back to Chem 400, if you took it at Sac City College, we did a lab with antacids, and we digested those antacids with HCl. That was stomach acid, set to that pH of about 1.5 for the stomach conditions. HCl is in the stomach, so the blood buffer needs to be able to neutralize large amounts or relatively large amounts of HCl. Blood buffer needs to be able to neutralize relatively large amounts of HCl without changing pH. Without changing pH much. Of course, we said that if you add HCl to anything, the pH is going to go down. We just don't want it to go down very much. Any questions about that? Travis?
With the effective buffer ratio being over 10, what can we expect when we go above or below those effective buffers? Like, do they just cease to work, or do they work too well to the point where
Yeah, good question. So what does it mean to be an effective buffer, really? And in my mind, an effective buffer can neutralize both strong acid and strong base. That's what this term effective means, and that's why there's a limited ratio right here. This is a good buffer only against strong acids. If any strong base, so not that you would, if sodium hydroxide got in your blood, you'd exhaust that blood buffer quickly, and your pH of your blood would change quickly. There'd be other effects too. Don't ingest sodium hydroxide. Or don't let it get into your blood using that. But that's what I mean. So there are specific cases where you know what the challenge is going to be, so you can set this accordingly. But in chemistry terms, if you're making a buffer to keep a cell line alive, say, you're typically going to make it with equal amounts of conjugate weak base and weak acid so that it will be able to take challenges from either side. Now, one of the things we're going to do in lab is we're going to prepare a buffer with a given pH. Say 500 milliliters of buffer with a pH of 9.10 and a total concentration of 0.10 molarity. Step one, we'll do this in lab, and you'll see this actually. I've written a problem like this on the homework as well, a problem or two. Choose your weak acid to be as close as possible to your desired pH. So ideally, for a good buffer, your pH equals your pKa. So we're going to try and set this as close as possible. 9.10 equals our pH. We're going to want to choose the pKa of our acid that is closest of our choices. So what I do is, I take this pKa, I do 10 to the minus of it. 10 to the minus pKa will give me the Ka that I'm looking for. If I do that, 10 to the minus 9.10 is 7.9 times 10 to the minus 10. And then you go to your list of Ka values and you look for them. And here's what we're going to do. Since I know what the answer is that I've got written on my piece of paper, I'm going to say something a little different. I'm going to choose the ammonia buffer system. And if I look for that, what I'll find is that the Kv value equals 1.76. Well, let's do this. Let's just use 1.8. 1.8 times 10 to the minus fifth. If I want to find the Ka value for my conjugate acid, Ka, for my conjugate acid, ammonium, times Kb for my conjugate base, equals Kw. Now, we gave this to you last time when we were talking about pH of acids and bases. Still useful, still very useful, in fact. So what you can do is, you know the Kb value, you know Kw is 1.0 times 10 to the minus 14. You can solve for Ka of your acid. Again, this works only for conjugate pairs, but I don't think you'd want to be doing it at any other time anyway, so it's a little redundant. I get 1.0 times 10 to the minus 14 for my Kw. I get 1.8 times 10 to the minus fifth. And I get my Ka value of 5.6 times 10 to the minus 10. not too shabby. And it turns out that this is a popular system to choose because ammonia and ammonium are relatively inexpensive to purchase. Questions about what I have so far? If not, step 2 is to calculate the total moles of weak acid and conjugate weak base. What that looks like is we know the milliliters, we know the molarity of the buffer that we've been asked to make. Calculate moles. We've done this before. You calculate the moles, and what's not obvious here, and you will know this, it'll talk about this on the lab when you do this for the buffers lab, is that that number is equal to the total moles of weak acid and conjugate weak base. So that's not obvious, that's a definition in fact. But that is part of designing and preparing a buffer. Step 3, calculate the moles of weak acid and conjugate weak base individually. We'll write out the Henderson-Hasselbalch equation. We'll plug in our pH, 9.10. We'll plug in our pKa. Well, we have our Ka so far. pKa in this case is 9.25, just the negative log of the K value. The pH of our buffer is below the pKa value. That means that whatever this log term is, it's going to be negative. For this term to be negative, that means that we have to have more weak acid than weak base. Now, before I write the next term, I'm going to define my moles of weak acid as X. So X equals moles of weak acid. And I know that my moles of weak acid and my moles of weak base equals 0.0500 moles. So my moles of weak base are just 0.0500 minus X. And this part is just definitional, so don't worry too much about this part. It'll allow us to solve for X really when we plug it in here. Otherwise, you have two unknowns in one equation, so that's what it's supposed to. Now I have one equation and one unknown. How many people feel relatively confident doing this math? A few of you. Well, I'll do a little bit more at least. Actually, I would allow you to do it for homework. We only have one more minute left and I want to get through this problem. X if you solve it, X is 0.0293 moles, which are moles of weak acid. Subtract it from 0.05, and our moles of weak base is 0.0207. And those are moles of conjugate weak base. And in the negative amount of time I have left, I will just say that our weak acid is NH4 plus, and our weak, and our weak base is NH3. So this is moles of NH4 plus. And thank you for sticking around for an extra 30 seconds or so. We'll pick up there next time. I'll be happy to answer any questions. If you did, first thing I'll do though is I will hand back any exams if you didn't pick those up, or get them passed back.